Okay, Assalamualaikum and welcome back again. So I think I have to apologize because my computer has become unstable. So let me just mention briefly what we have already mentioned before this in the. Are you seeing the notes? Right? Am I muted or what? Are you hearing me, guys? Okay, please unmute yourself and because I could not see your messages. Okay, so let me just restart with a correction that I mentioned before. I was mentioning exponential I pi at the end of the last lecture in the recording, which is +1. That is wrong. It's actually equals to -1. You get plus or minus 1 by taking n equals 0 and n equals to 1. Okay, so I think that should clear things up. And then today, as I mentioned earlier, we have in this particular section, we are doing powers and then the inverse of powers, which is the n root, for example. And then if you have your variable or the complex variable become an exponent over here, then one should be talking about the log. So if it's 2 over here, then it will be log base 2. So if it's exponential z, then you talk about the natural log, or sometimes it's called ln. So I will just say log without no when I use this notation, it's the natural log. Okay. So again, this we have already done, and one the complication about log. Let me just see if this works or not. Okay, it doesn't seem to work. Okay, never mind. I don't want to stop the recording anymore. One of the problems with this log of a complex number is that you get multi-valued functions. So then usually it depends on the situation. Sometimes you want to have the multi-valued the multiple values. Sometimes you need that, but sometimes you just want to have a single value. Then you go to what we call the principal branch, which I've already mentioned in the previous lecture. So today we're going to look at the inverse function of sine. Okay, sine is given in terms of your exponential previously with this. So when one takes the inverse of sine z, then you will be getting z, but then you'll be getting also sine on the other side. Okay, or here if you want to. Then you essentially you need to define what this sine of a complex number is. Okay. So we look at a particular example. Let's see if this still works. Okay, great. Now, here you are given z equals to sine 2. Either you be given that or you are given sine z equals 2, and then you have to find out what z is. Okay. So the best way is to look at sine z in terms of the exponential, because then you already have learned about the law of complex numbers. So then what one does is to rewrite your sine z as that, okay, and equate this equals to 2, and then you simply try to what you call solve this equation. And how to do this is to here, remember in the sine you have exponential iz and exponential minus iz. So if you write your exponential iz as u, okay, then your exponential minus iz is actually u inverse. So now we can write this for the time being as u minus u inverse over 2i, and then you rearrange the equation, then it becomes an algebraic equation which you can actually solve. So you get u squared minus 4iu minus u equals 0. So this is just a quadratic equation that we have seen before, and you know how to solve quadratic equation. So you just simply use the quadratic roots formula, and you'll find that, okay, I get my answer to be this. Okay, but remember that this is not your z, this is your u. Okay, you're solving only for u, which is now was defined earlier as exponential iz. Okay, so we need to undo this, we need to consider this equation now. Okay. This equation saying exponential iz equals to this complex number, but then I know what's the inverse of that. Okay, so I'll take the log of exponential iz equals to the log of I2 plus or minus root 3. Okay, and this one will just give you z equals to the same thing. Okay, so all we need to do is to find out how to define this log of this complex number. Okay, so here we have done it below. So remember to do the complex number thing. One could directly use that, or one could simplify this further by noting that this is actually this complex, this imaginary number I multiplies with that, and I can separate using the log additivity property. Yeah. So I get log I plus log 2 plus or minus root 3. Now this is simpler compared to this. Otherwise you can also directly from here, then you take this complex number, find what are the polar form for that. You can do that if you want to, but I have done it in this particular way. So there are many ways to solve this. Then one has this log I, which we can write as exponential I pi over 2. Remember, exponential I pi over 2 is equals to that's okay, exponential I pi over 2. Let me just write this. I'm getting a bit upset for today. Cos pi over 2 plus I sine pi over 2. So this is just equals to I, right? So I can do that, but remember I have this multi-valued properties, so I put this as well into the exponential, that 2n pi thing. Okay, so I have that. So in other words, I will take the log of I to be equal to that, and log of the exponential is just giving you the phase, or the thing that appears in the power. So I get I pi over 2, and then you remember one also add in this multiple valued thing, so that you get all possibilities. Okay, so you get this thing from that. Now what's left is to evaluate what this is. Okay, so this is essentially a real log, so you know how to do that. So I could just simply find out what this number is, and then take the log of that. But now remember, there are two different values inside this real log. So here is another trick that one can actually use. The fact that your log of 2 plus root 3 inverse, okay, is well, I mean, this is the number, the original number, okay, 1 plus over 2 plus root 3, that's the 2 plus root 3 inverse. But now I can simplify this number by multiplying with the, not to say the conjugate, the one with the, here if it's a plus third, then I will just multiply with a minus third, top and bottom. So this becomes 1. So you just multiply by 1. Then I will be able to remove your third at the denominator and makes the number simpler. And in this particular case, you get the square, the difference of the squares, 4 minus 3, square root 3 square is 3. So you get 1 at the denominator, and then what's left is the third appearing on the top, which is log 2 minus root 3. And this is precisely the two values, one of the two values that appears here. But now what this is, now you can simply use this part of the what you call expression and bring your powers to the front, right? So you get minus log 2 plus root 3 equals to that. So what happens in this particular case, I am able to write log 2 plus or minus root 3 equals to plus or minus, was it plus or minus plus or minus log of 2 plus root 3. Again, this is not really necessary, but one of the things that could happen in a question, whether it's assignment question or test question, is to make your answers, your solutions, to be the simplest as possible. Okay, so this is one of the ways that you can actually do all the manipulation. So finally, you get this particular answer, now given in terms of a very much less messier thing. So you get plus or minus again over here, but now not only includes 2 and pi, but you includes this imaginary part. Okay. So let me do the last one. The last one is to, sometimes what happens is that when you do integrals, this is just an application of the log function thing or arcsine function thing. Sometimes when you do an integral, you can get different expressions for the integral. So one of the things that we already have done by identifying this integral is essentially your arc hyperbolic sine or arcsine. Okay, so this integral is equivalent to that, and that essentially uses some substitution method to do that. Okay, so this you probably have to look up some old calculus thing. Okay, but you can see also from the standard tables that this is written in terms of that. So now one needs to understand how is this equivalent to each other. So what one does is to write this in this manner. So you write your z as this arcsine of x over a, and then arcsine, sorry. Then you have x over a equals to sine z, which is now written in terms of that. Okay, then you use the same technique again. This is just equals to u, this equals to u inverse, and then you're going to solve again your quadratic equation by rearranging this equation. Okay, so then you'll be able to get this so-called solutions of the quadratic equation. then what happens over there is that given that usually what happens here, okay, sorry, here is essentially an integral which a real integral, okay. So the solution that we want is actually a real solution. So in the things below, so you had this possibility of two different sign, but this is because we enlarge the definition of the integral, enlarge the problem to a complex domain. Then you get essentially two different solutions. But for our case, we choose the positive root because for real z, then your exponential z is going to be greater than 0. So then if you take the log of that, then you get your z, okay, and you find that your z equals to log of that number minus the log of a. Okay, so in other words, the difference between the two, okay, the difference between this form and this form is just this particular constant log a. So there sometimes one adds a constant of integration in such a way to simplify this expression over here, and then you'll be able to write this in terms of your arc sine. Okay, so that's why you can have sometimes different expression just because of the manipulation of the constant of integration. So that more or less finishes this particular lecture on complex functions. So the next topic will be something on algebra. I will start just a little bit, and then I will talk about your first test. Your first test after I introduce the topic. So the lecture file is coming from I think about something going on. Okay. Somebody coming at the end of the lecture. That's clever. Right. So this will be the chapter after the complex numbers, I think. So this will be chapter 3, if I'm not mistaken, from Boas. So we are going to, there are a lot of topics inside this chapter 3 of Boas. One of them is matrices, and then one of them is linear equations. And then from matrices, we also talk about determinants. Why I did lumped into a single chapter is because they are related to each other. Okay, so essentially the idea here is that this particular chapter is essentially on algebra. Algebra itself is actually comes from an Arabic word, al-jabr. Okay, I do not know how to pronounce the Arabic word, but never mind. It has a particular meaning, but there most of the time, it talks about how to solve an algebraic inequation mostly. Okay, so algebra has become a name in a broad branch of mathematics, and essentially just studies symbols and their manipulations. Okay, so when you, for example, when you write down the equation, sometimes you replace this by a variable which is written in terms of a symbol, and then these symbols are being manipulated to get solutions. So that's essentially what it is. Okay, and then a subset of this algebra. Okay, the algebra consists of many different mathematical structures that one can look at, including matrices. Okay, linear algebra essentially another branch of a sub-algebra, sorry, a sub-branch of algebra that studies linear structures. We shall define what this is later on. And these linear structures are related to another structure in mathematics called vector spaces. And generally we call this as linear spaces because of this fact of the space obeys such linear structure. Okay, and you have seen vector spaces before. They are just space of vectors. I hope you have done that. Okay, the concept of vectors that you introduce is to extend scalars, which are usually represent numbers. Okay, and in fact vectors are not only the possible generalization. Later on, probably if you do the second course on mathematical methods, usually it's named mathematical physics, you will see that your vectors are in fact a subset of what is known as tensors. Okay, this will you learn later on. Okay, and one of the things that we have learned in vectors before, we reduce this by saying that okay, we represent this in terms of components. So we have Vx, Vy, Vz, which are the x component of the vector V, y component of vector V, z component of vector V. I believe you have done this very much earlier, or at least in your first year at least. Okay, then one of the things that happens is also you can represent these three components as a set of entries inside your matrix. So another way of representing this equation, for example, is to write it in terms of a column matrix. Okay, so you can see now the relationship between matrices and vectors easily by thinking of this as a 3x1 matrix. Okay, and the other thing that we also learn when we do vectors, there are two basic operations. One is called a vector addition. You take two vectors, you can add them together. Usually when in terms of components it will be easier, but let me just write this in this way. For example, you have this V as representing a particular arrow with a with a magnitude there, and then a W over here. Then sorry, it's not drawn properly, but essentially the vector U will be given by this diagonal. Okay, so you can see that okay, the resultant of this addition, and in fact, no, what does it mean by this addition? It means this arrow is joining up this arrow in this particular way. Why it does have to be that? No, this is again some of the definitions of mathematics that seems to come natural in that sense. But there's a reason for why you do that. Is because let's say this is V, this is W, and this is U. Then I can reverse this. It's not drawn perfectly, but I can now write this as W plus V, sorry. Okay, so in other words, this is the same thing. And this is probably, if you have learned this before, this is what we call the parallelogram law. But this idea and this thing is called what we call commutative under addition. That means it doesn't matter how the ordering of the addition is. So these are specific what we call structures in mathematics. Okay, And that's why you have this definition of addition with these arrows in that way, because you find that no, it obeys this parallelogram law, which is essentially saying that the vector addition is a commutative operation for which you can actually swap the vectors around. Okay. But it's much easier for us to look at in terms of matrices in this way. For example, then you can see that, okay, V plus W, you just write V as this 3 by 1 matrix and W by another 3 by 1 matrix. And how do you add this? Again, this is something that you feel that, okay, this is simple enough. But actually, there's a lot of things going around this operation. But you know what it is. It's just saying that, okay, the components add up, just like Vxi plus Wxi, then you just simply have Vx plus Wxi. And they are pointing all in the same direction. So you get this thing. Okay? And the same thing for the second component and third component and so on and so forth. And there you can see that this is also the commutativity is much obvious over here, because you have these are just numbers now. And this is just saying that, okay, this is the same as W plus V. Okay, so that is one of the basic operations inside your vectors. Usually I call this vector algebra. There is another operation called the scalar multiplication. So normally the vector operation has this scalar multiplication and vector addition, and the scalar is depending on what number that you use. If you use the real numbers, then we call it as a real vector. If you use a complex number, then it calls a complex vector. But that we can do this later on. Okay. It's now 5 minutes more to the end of the lecture. So let me stop at this stage, and I will go through again this particular part, because we want to extend this to the case of the general matrices. Okay. So let me go here. First, I will take your attendance. And I will discuss a little bit about your first test. Okay, I've just talked to Dr. Nizam this morning. That's done. And your first test will be in the 5th week. Be on the Monday, because on Monday we have a 2-hour class. Okay, so that then you have a bit more time to the test. Okay, so we'll have yes, is there a question? Okay, so this is week 3, right? So week 3, week 4 is next week. So I'll be hopefully I'll be giving you a first assignment by the end of the week. Okay, and then you need to submit that during the next week. Okay, and then you'll get the solutions after submission, and then we can have the first test. And the first test covers your series and the complex numbers. Any questions about that so far? Please say yes or no. Oh,
How many questions are there?
okay, I cannot tell you now how many questions are there because we have not set up the questions, but essentially it's going to be 1.5 hour test. At least that's the way we have done in the past. So again, I've not discussed this with Dr. Nizam in detail as yet, but we just set the time for week 5. Okay, so week 5 on Monday during the class time. Okay. Okay. So I'll be giving you the assignment. Please, for the assignment, somehow I need to do something like this. I need you to group yourself in pairs because there will be many questions. Okay, and then you submit your assignment as a group of pairs. Okay, is that okay with you? Then you can subdivide the different questions among yourself, and no, you can start to save time in that sense. Is that all right? Say yes, or otherwise you have to do this. Okay, otherwise you have to do this. Okay, so we do it in groups of twos, and then we see what happens. Okay. Okay, that's all for today. Thank you, everyone. Yes?
I have a question.
Yeah.
For the test, will it be online or physical?
It,
It will be online, is it?
as far as we have no updates on what's going to be, but I think it will be online. Most probably it will be online. Okay. So in other words, the test will essentially an open book test, but you have to do it within say 1.5 hours. Okay. So for the assignment, please find your partner and then subdivide the different questions among yourself to do it. Okay, that's all today. Thank you, everyone.
Thank you, Doctor.
Bye.